Okay, so this is a really important one, AES Modes. So what I showed you before was electronic codebook, right? And so in electronic codebook, what I mentioned is that if you have some input, so if I had A, it's always going to map to whatever the BCD, whatever the output is, right? If I put in A here, again, it's going to map to the same thing. So you can imagine that's bad because if someone discovers what one sequence means, they can decrypt that sequence anytime they see it now. So this is typically not a great usage of the algorithm. We can see this very obviously if we take this, kind of famous example that's used in a bunch of spots now. We take this friendly penguin here. So this is the Linux tux, if you haven't seen that. We take this friendly penguin, we apply AES-ECB in order to hide them from our adversary, and we get a scrambled image. Oh no, right? This looks almost exactly like the penguin. What happened? That doesn't look encrypted at all. Well, what's happened is that because it's ECB mode, right? If you have like a certain color that's stored as a sequence, like black or whatever it is, yes, it's translated to something different. So we can see the colors are different or off, but it's always translated to the same different color. So obviously this means that our security isn't very good because the overall structure is still there. And in this case, because it's an image, it's really obvious that the structure is there. So in general, though, if it's not an image, right, it's still very bad because if you find out anything about the block, you're still going to be able to decrypt anytime you see that. So what we want to expect is like this. So this looks like just random data. And we can accomplish this by using what we call modes of AES. So the first mode that I'll talk about is Cipher block chaining. In Cipher block chaining, what we would have is we'd have our input. So this is tux image. And we actually, rather than directly putting it through the cipher, so before, remember, all we did is we directly put it through the cipher. Oops. There we go. We're going to XOR it. So this little thing here says we XOR each byte with something else. At the start, we XOR it with an initialization vector, which is basically just a random sequence of 16 bytes that ensures we have different starting points every time we run it. After that, we actually XOR it with the previous output, right? So this changed the ciphertext in sequence, and we no longer have to worry about this as much. So now the same input data, right? If we had A here, well, it's being XORed with something, it's generating some other output, and then that other output is being XORed with the next input. So it's always changing what the input is. And if we change the initialization vector, then again, it's going to fully change what the sequence is. This random initialization vector is not a secret, right? So normally it would be transmitted in a way that the receiver is able to get access to it because they need that to decrypt the data. The decryption algorithm needs that IV. But ideally it's random, so it's not reused. AES-CBC, as a few of these are vulnerable to bit flipping. So if we change a bit somewhere in here, it's going to create garbage at the output. But that one bit change, right, is going to be XORed with the output here, which means that will actually affect 1 bit of the plaintext. So I mentioned that in the previous section when why we want authentication as well. So another popular mode is counter mode. So there's a few modes I'm not covering. I'm just kind of trying to hit some of the popular ones. In counter mode encryption, what you can see is we actually encrypt not our input data. So our input data is down here at the output. We encrypt a counter, and that counter basically increments for every block that we encrypt. So if we started a message, right, a long message we're encrypting, we'd start at 0 and increment it every time we have a new block. Note super critically, there's this nonce, and this nonce is just random, is a random data that guarantees we're generating a different key stream. Because if you look at how this is constructed, basically what you have is this block cipher here. Oops, come on. This block cipher here is more or less generating a stream of some data that's being XORed with your plaintext to get your ciphertext. So this sounds a lot like a stream cipher, and it basically is a stream cipher. The sort of nice thing about this is that the decryption is actually the exact same thing, because the decryption is just going to generate that same stream cipher, or that same key stream, and XOR it in with the ciphertext instead of the plaintext. So, you know, the only difference here is where the plaintext and ciphertext is between decryption and encryption, right? So it's just the plaintext and ciphertext switching spots. So that's sort of nice because it reduces how much structure we have to have. The other thing we have is, you know, previously we called it initialization vector, IV. Here we have this number used once, or nonce. It's incredibly critical with counter mode that nonce is not reused. A nonce reuse problem basically allows a substantial advantage for an attacker. And why this is that if you imagine, because we're generating a key stream, if you look at the input to this block here, notice it does not involve anywhere in that red circle your ciphertext or your secret data. Thus, if you rerun the encryption with the same nonce and the same counter, it's generating the exact same key string, regardless of what your secret data is. And the big problem here is because the key stream will be the same, the attacker could know that. So if they figure out that, hey, there's actually an error, the nonce could be reused because the device takes the nonce in from the user, or when you reset the system, the nonce is always the same. They could have a situation where they have a known ciphertext and plaintext, right? So if you knew the ciphertext and plaintext, so let's imagine you know here and you know here at A and B, right? Well, A and B are just XORed together. Normally, the key stream is XORed with A, right? So we normally have key 0 XOR with A0 equals B0. Well, if we know A and B, but we don't know the key, we could just say B0 XOR with A0 equals key 0, right? So now we know what that key stream is for that first block. Normally that wouldn't matter because that key stream is never reused, but if the nonce is reused, then that key stream ends up being used somewhere else. And then I could use that to decrypt something where I don't know the plaintext. I only have the ciphertext. The other example, right, is that, so imagine again, we had this AES counter and say a communications interface, fairly common in these. If every message, let's make it a worst case, right? The nonce is reused the same on every message, it just reinitializes it to the same value. Well, you could just force a known message. So you could send a query to the device where it responds in some way that you know what the answer is. You record the ciphertext, right? Again, you go message XOR ciphertext, gives you the key stream. And then you record unknown messages and you can freely decrypt them. So AES counter mode relies on a simple structure, which is the advantage because it's easy to use that structure in practical situations, and you only need that one implementation. Provided nonce reuse is enforced, so or you can enforce that it's not. It can be enforced to not happen, I should say. Right? We don't want it to happen. It is a good choice. And one of the advantages compared to like AES and CBC mode is that it can decrypt arbitrary blocks, right? So if we look back at CBC mode, one disadvantage is that AES-CBC depends on the previous ciphertext. So with AES-CBC, you cannot decrypt arbitrary blocks, without having some access to the previous blocks. So what you can see, right, is that if I want this plain text here, well, it relies on the ciphertext, you know, the -1, the previous one, in order to decrypt it. So either have to have access to that ciphertext, or it has to have presented as the entire stream. So that's kind of the only disadvantage with AES-CBC mode, which of course depends on the use highly. Yeah. So with AES counter mode, right, all I have to provide is the counter and the nonce. So if there's a way that prevents the attacker from being able to arbitrarily force nonce reuse, and they can just go to some block number, you can automatically decrypt that arbitrary block. There's a newer mode called Galois counter mode, GCM, and what this provides is the initial, so the diagram looks a little different, but this part here is the same. So you can see there's a counter, right, that goes through the encryption. It's XORed with the plaintext to generate the ciphertext. So this is part of the encryption. What's new, or what's different, is that it also adds some authentication capability. So what this means is it actually combines, what you're basically doing is you're combining all of the ciphertext together. So you can see that the ciphertext is XORed with, and so this is where there's multiplication of the Galois field. And we have data that we want to authenticate as well as the encryption. So this might be like the header or something like that. And we can basically, it chains together all of the ciphertext output such that we end up with what they call an authentication tag. So this authentication tag is a number that will cryptographically depend on what the data that was just decrypted. So what this is perfect for is it avoids the issue of these bit flipping attacks, because if you look at AES counter mode, of course, with this ciphertext XOR plaintext construction, if you change any bit in the ciphertext, right, it's going to flip in the plaintext as well because it's all just XORed together. So we still have that bit flip problem. The Galois counter mode adds an authentication tag, so it doesn't prevent it at the algorithm of the actual decryption. It provides an additional feature, which is a tag, and we can basically confirm that this tag matches. So we can confirm that the authentication tag that's presented in the data is going to match the one that we calculate, and thus the whole system works. The data was not modified in transit. So GCM provides us with the additional feature of giving us the data integrity as well as the data confidentiality. It's not the only AES mode that does that, so there are other AES modes that provide it. It's become one of the more popular ones lately, so that's really one of the reasons that's worth bringing up here. I also should mention this crazy sounding one, XOR encrypt XOR base tweaked codebook mode with ciphertext stealing. You'll see it just called XTS, AES-XTS. This one is used extensively in hard drive encryption. And basically what you have is up here is like a hard drive sector number. And this sector number, you can see it's kind of a bit like a counter mode. And what we have is we actually have a tweak. So the idea of this is that we have this tweaked codebook is where the tweak is actually dependent on the area of the hard drive we're accessing. So we add some tweaks in that basically depend on the sector, and I guess I'm cutting off some of the name here, that depend on the sector we're accessing. The other thing it adds is, you'll notice, so the ciphertext stealing, you can see there's a little extra chunk of ciphertext here, and what's going on here, it's getting shoved into the plaintext at the end. This is actually to work as a padding. So if we are decrypting less than the full block length, right, because the hard drive sizes, sector sizes, may not end up being the same as the AES block sizes, right? So these are designed for totally different things. What we have here is that the design of the algorithm is designed to sort of marry the block size of the cipher with the hard drive, whatever the sector size or whatever the limitation of the hard drive is. And so it provides, you know, a lot of the features that are needed here. So there is some different modes that you might run across. This is very unlikely. Like, I don't think you'll see this in like an embedded device for anything, but this is extensively used in basically all hard drive encryptions. Yeah, so that's just what I said here. So yeah, that's just a quick summary of some of the AES modes. There's several modes you could use. The real takeaway is do not use AES-ECB, right? If you're encrypting a large block of data, basically more than one block of data, because any block of input data with ECB is always going to map to the same output data with the same key. So the suitable mode will depend a little bit on your usage requirements, right? If you're building a hard drive, well, XTS would make sense because that's the standard. If you're doing a communications interface, counter mode is used extensively for that, you know, and maybe you want with authentication, so GCM, et cetera, et cetera. So it's going to depend on your requirements, but it's important to know about the modes and know how the fundamental blocks are used to build these more complex modes up out of them.